Okay, all yours.
All right, great. So yeah, thank you everybody for joining. This is our third seminar of this series, by the way. So this meeting is being recorded, and we have, for those who want their meetings recorded, YouTube links on the website if you want to look at previous talks. But yeah, without further ado, we're very happy today to have Panayotis Mertikopoulos from the French National Center for Scientific Research present to us a unified view of learning in games. Panayotis, please, you have 1 hour, including questions. And after that, for anybody who wants to stick around and has time, we have open-ended discussion. Take it away.
Super. Thank you very much. Thank you very, very much also for having me. It's a pleasure to be presenting in this seminar. And you know, the title I struggled a lot with the title. It should be towards a very subjectively unified view of some learning frameworks in games, but then it grew too much. So I opted for this, and because I see also Bernhard in the audience, I should say that this is based on a chapter that I owe him for a very, very long time, and he's been very, very nice to to not pressure to not put the screws on me, and I appreciate this. Just to let him know that I have not forgotten, and it's not for. So I'm hoping to give you, Bernhard, a preview of what will be in there. But also, I should say that what I'm going to be presenting today is by no means my work or my work alone. It's been done with in collaboration with a lot of brilliant people. Three of the youngest you see here: Victor Bon, Angel Guillano, and Yaping Shi. He's sipping here some coconut water. And the motivation for all of this, or at least my motivation and the motivation of certain of my co-authors in this has been, yeah. Oh, okay. Okay, sorry, I thought there was a question. The motivation has been some of the modern applications of game theory, particularly in machine learning and AI, where you have games being used to model such systems as generative adversarial nets, or more interestingly, I guess, for this workshop, multi-agent reinforcement learning systems, MARL systems like autonomous vehicles, etc., but also the type of recommender systems that go into network routing management systems and the recommendation platforms like Google Maps and Waze, etc. Now, just to be clear, I don't want to get into the details of these models. This is not the idea of this talk. This talk is going to be theoretical. I just want to mention this for motivation. And instead, I just want to highlight the common unifying theme of all these applications, which is that in all of these you have several agents, each with their individual objectives, such as selecting a route to go from home to work. And the payoffs in these cases are determined by the actions of all agents. So we have a game of some sort. So, for example, in the traffic routing case, you would be encountering other commuters on your choice of route. And then once you observe your payoffs, once you get to your payoffs, you will get the chance to adjust your actions, and the process repeats. And how the process repeats will be part of the learning process, or will be part of the more general game framework that is being played. And in all cases, I'll try to be as inclusive as possible. The driving question that we want to answer is, what does the agent's long run behavior look like? All right. So I'll try to basically set the stage for these questions with two driving examples. One is going to be from finite games, ordinary finite games like rock, paper, scissors, matching paintings, and all that. And the other is going to be from stochastic games, and in particular policy gradient methods. So I'll slowly build up to this. But before I do, I'm rather just to formalize what I was just saying before about how the learning process works, is that we will always consider a variation of the following sequence of events. All right, there is some time variable which evolves over time. This could be either continuous or discrete. For most of the talk it will be discrete, and at each instance, every player, every participant in this decision process will be choosing an action. Based on the choices of action, they will be receiving a reward. Then they may be receiving some extra feedback or not. This depends a lot on the model, the specificities of the model. This may be the case, or maybe they just observe their payoff and that's that, or maybe they don't even observe that information and there are delays, whatever. Uh, and then this is a loop that goes on and on and on. All right. So the defining elements of this process are always going to be time, how many players there are, whether we have a continuous or a finite set of players, actions, what type of action sets the players have, what is the reward structure of the game, whether the rewards are only determined endogenously in terms of whether they are defined by the interactions of the players between them, or there is some exogenous influence from nature or the environment. And of course, as I said last, feedback. Okay, what type of feedback the players receive? Do they get to observe a lot of information, their entire payoff vector, some noisy version thereof, only their payoff? What? So there are lots of modeling choices here. And of course, this gives rise to a very wide and flexible model. For this talk, we will be talking about processes that evolve in discrete time in one way or another. The set of players will be finite. Actions, well, we'll see. We'll start with finite actions, but then we will quickly migrate to continuous action sets, and you will see why. And for the reward process, we are going to ignore the influence of some outside player that is not being affected by the players in the game. So we're also ignoring all Stackelberg type games and all that. All right. So if we apply this template to finite games, so in a finite game, we have a finite set of players. Each player has a finite set of actions, and players are also, this is something which is new relative to the previous framework. Players can be mixing their actions, so they can be playing mixed strategies, and given a mixed strategy, then they draw an action like rock, paper, or scissors based on this mixed strategy. Okay. Now, the type of feedback is going to be classified here in terms of rather a very useful quantity to classify their feedback is going to be their mixed payoff vectors, or more concretely expressed as the individual gradient of the player's mixed payoff function. So if everyone plays xi, a player I plays xi, all other players play x minus I, and we concatenate them into a mixed strategy profile x. And if ui of x denotes the player's mixed payoff under the mixed strategy profile X, then the mixed payoff vector of the player is simply the gradient of this mix of their mixed payoff with respect to their individual strategy. And because of linearity, because the dependence on everyone's strategy is linear, this gradient is also equal to the vector of mixed payoffs, to the player's vector of mixed payoffs, meaning for every one of the player's individual pure strategies, what would that strategy have given against the mixed strategy profile of the player's opponent? All right. So this quantity, this individual payoff gradient, will be crucial in determining the type of learning process that we have. In the most benign, in the full information case, we will be assuming that players have exact full information on this vector. All right. Now, this is usually too much in terms of information, requires too much in terms of observation, for instance, of other players' actions, or even the full matrix of the game, which is not known in general. So this is usually relaxed to knowledge only of the vector of their realized payoff vectors. So these are the counterfactual what-if payoffs of each player given the actions that other players actually chose, all right? Or worst case is you play, you do not observe what other players chose, and you only get information about your payoff. You only get your payoff, your reward, and that's that. All right. So these are three very different feedback structures that we will try to integrate in our learning framework. Mixed payoff vectors, pure payoff vectors, and bandit type or payoff based feedback. All right. I have here an example of what exactly these types of feedback structures give in a simple game of rock, paper, scissors. But at this point, I think instead of going through the example, I mean, you will have my slides so you can look at it if you're not familiar. I guess this is okay for this audience and I can skip. If not, just shoot me a question. I'm very happy to explain this in more detail if it's not clear. All right, I don't see any nays, so I'll just skip forward. And I want to see how we actually use this type of information in practice. And one standard method, I understand that Galit showed in the inaugural seminar. Galit, I think you talked about fictitious play. Fictitious play as an algorithm is a bit different in practice because you kind of know the structure of the game, and you're best responding to the empirical frequency of play of your opponents. Here, the algorithm that I'm showing here, and which is part of a big template known as the exponential or multiplicative weights template, and original due to Lilson and Wormuth, and then Peter Auer, Nicolo Cesabianchi, and their co-authors in the 90s. This algorithm does not work based on best responding to past frequencies of play or something like that. Instead, what does it do? Let's say that you start with some mixed strategy and you're drawing some action, and based on this action, you're getting some version of the feedback vectors we talked before. So maybe you're getting full information about the mixed payoff vector. Maybe you get your pure payoff vector, or maybe you only get a scalar worth of feedback and you have to somehow reconstruct in a smart way an estimate of your mixed payoff vector. All right. This last thing, what I said, reconstructing your vector of payoffs from a single observation. This is not something that I'll go into. There are standard constructions how to do this. I'm not going to go into this. But at least this is what I mean when I'm saying that you have banded information, but I'm referring to vector feedback. But anyway, you get some estimate of your mixed payoff vector, and then what you do is you aggregate this estimate. So you're basically taking a step along the direction of your individual payoff vector, and you're constructing this process. This is sort of a score, an auxiliary process. And what you do, you need to get a mixed strategy out of this process. So what you do is you kind of project this strategy, this score variable, this score vector, rather, back to the simplex, but you do it in a smart way. You do not use Euclidean projections. You do not just take the Euclidean projection back to the probability simplex. You use this more refined exponential mapping, which tells you that the probability of selecting an action is exponentially proportional to the score of to its propensity as constructed, as derived from this score vector. For those familiar with the work of Earl and Roth in the 90s, this is the stimulus response. This is rather a stimulus response type model, etc., etc. All right, but basically the idea of the algorithm is this, that you score actions by aggregating the payoffs that you observe or that you estimate for them. And then you employ an action with probability which is exponentially proportional to this score. If you have full information, this algorithm is known as hedge. If you only have bandit payoff-based feedback, this algorithm is known as EXP3, exponential weights for exploration and exploitation. And there are lots of variants, etc., etc. Okay, I will get back to this algorithm later. But for now, what I want to do is that, okay, we have this algorithm. And what we would like to do is to examine what are the properties, what is the behavior of the players if they follow this algorithm, and in particular, if they somehow equilibrate over time. So to do that, let me very quickly introduce the notion of a Nash equilibrium. We introduce it in the standard way. So at a Nash equilibrium, no player has an incentive to deviate from their chosen strategy if all other players stick to theirs. And this is just, I mean, this is just the formulation of a Nash equilibrium in mixed strategies. What is more, some terminology and one important distinction that we need to make depends on the support of an equilibrium. If the support of an equilibrium is a singleton, then we are talking about a pure equilibrium. All right. And if we have here in the defining inequality of a Nash equilibrium, if instead of a weak inequality, we have a strict inequality whenever, of course, xi star is different than xi, then we talk about strict Nash equilibria. All right, and strict Nash equilibria are necessarily pure, so their support is always a singleton, and they can be characterized equivalently by saying that at a strict Nash equilibrium, each player has a unique best response. All right, so these are basically the main distinctions we want to make. We have the notion of a Nash equilibrium in mixed strategies. If the support is a singleton, we talk about pure equilibria, and if the inequality, the defining inequality is strict, then we're talking about strict Nash equilibria. Why am I insisting so much on this distinction? We will see that this distinction has a crucial role to play when it comes to learning. And much of it has to do with the geometric or variational structure of different equilibria. All right. So if we have, oh, that's a typo. That should be an X. Sorry about that. So if we have a fully mixed equilibrium, which means that the support is the entire set of pure strategies, then it is somewhere in the interior, in the relative interior of the player's probability simplicity. So the situation looks like that. If it is mixed but not fully mixed, it is somewhere on the boundary of the simplex, and it has the property the defining inequality of a Nash equilibrium implies that the player's payoff vector is actually going to be orthogonal to the simplex at the point in question. And not only that, it will be orthogonal and outward pointing. So it will belong to what is known as the normal cone to the simplex at said equilibrium. All right. Now, if we're talking about a pure equilibrium, then things are a bit different there, because in that case, the normal cone is has a lot is full-bodied, has a non-empty topological interior, and again, the payoff vector at equilibrium always belongs somewhere in this cone. A strict equilibrium differs from a pure Nash equilibrium in that for strict equilibria, the payoff vector, the player's payoff vector at equilibrium belongs to the interior, to the topological interior of this cone. And pure equilibria are the only points where such a thing might happen, because pure equilibria occur only at the corners of the simplex, and the corners of the simplex are the only point where the cone is full-bodied. In all other cases, it has empty topological interior, so you cannot have a payoff vector in the interior of an empty set.
Can I ask?
Yes?
But normally this cone is can have a maybe not full dimension, but it has different dimension depending on the support, right? Because
Absolutely.
I mean, so it could be I mean, like it's flat if it's not the pure equilibrium, but it could be a lot higher dimensions. For instance, if you only mix two strategies rather than all of them, correct?
Just to be clear, the normal cone, the dimension of the normal cone, of course, depends on the support of the point where you are, but at every corner, every corner of the probability simplex, in all corners it has the same dimension, and it has the full dimension, which is the product of the player's action sets.
Yeah.
All right.
Yeah, sure.
Okay. I'm not sure if I answered your question or if I didn't understand it.
If you're fully mixed, there is no cone at all. It's just zero dimension.
If you are fully mixed, you still have a cone. It is the vector of 1, 1, 1, 1,
Oh, I
which
see.
because you're embedding the simplex in the orthant, so you still have a redundant direction, but that's it, basically. But yeah, now from a strategic point of view, this observation about strict Nash equilibria is very important. Why? Because it means that if you slightly perturb the payoffs of the game, then a strict Nash equilibrium, if the perturbation is sufficiently small, will remain a strict Nash equilibrium. Why? Because you will be simply perturbing a bit the position of this payoff vector. By contrast, if you perturb any other for any other type of equilibrium, you can find a nearby game such with a payoff perturbation which is arbitrarily small, which makes this point no longer be an equilibrium. Of course, it may just have moved by a tiny amount, but it will still have moved. All right. So on the other hand, strict Nash equilibria are the only ones that are stable under payoff perturbation of the original game, and this is the first time that I will mention that I will do a callback to the work of Kohlberg and Mertens in the 80s, who were examining the strategic stability of certain equilibria, and strict Nash equilibria are, of course, the only ones that have this property. All right, now keep this in mind. We will come back to it later, and we will see how important this is later. All right, from a learning viewpoint, we can forget for the moment about this question, and what we still like to understand is, when does learning, for instance, following this exponential learning algorithm that I showed you, converge to Nash equilibrium? When does it not? And what other types of behavior emerge in the long run, and whether these types of behavior are rational, rationalizable, whatever. All these are the type of questions that we would like to examine, again, in the context of finite games. All right. So I won't answer this question. I want to restate the same questions, but now in the context of a stochastic game, and follow basically the same order of presentation to try to draw a parallel between some questions that arise in finite games and some questions which might seem completely unrelated, but I would like to establish some similarities in the context of stochastic games. All right. So a stochastic game will follow Shapley, 1950s, 1953. What do we have? We have a finite set of players, finite set of actions per player. All right. And then a stochastic game is something which has an episodic nature and has time built into it, in contrast to a normal form game, which is a static entity with no time at all. Here, what happens is that as time goes on, at every state, nature is at a certain state. This is the state of the world and determines the stage game, the game which will be played at that stage. All right. Before going into the details of the stage game, at every state, players select a mixed strategy based on the state of the world that they observe. This is their policy. They have a mapping which takes states into mixed strategies. This is going to be their policy. It is, and we're only going to be talking here about stationary policies. So keep that. Keep that in mind. And then, based on this mixed strategy, as before, they draw an action. Then they get a payoff, which is determined by. Oh, whoops! That is a typo. This is S tau. They get their payoff depends on the action of all other players and the state of nature, which determines the stage game that they are playing. So depending on if it's raining, maybe they're playing rock paper scissors. If the weather is good, maybe they're playing some other thing, reaction game, whatever. Once they receive their payoffs, then based on everyone's actions and the current state, nature transits to a new state. It does so following some transition matrix, so there is an underlying Markovian law. And actually, this is why in certain literature threads, stochastic games a la Shapley are now being called Markov games, if you have heard this terminology. But I will be sticking with Shapley's original terminology, stochastic games. And once nature transits to a new state, this whole process repeats. There's a twist that with a certain probability, the process stops and the episode stops, and that's the end of this particular episode of the stochastic game being played. All right, this is what I have here as a stopping probability. All right. In this context, what the episodic payoff, the payoff of a player during an episode is simply the sum of the payoffs that they got throughout this episode, and then you're taking an expectation over their policies, the transition matrices, etc., etc. All right. So just to make something clear, you will see here that there is no discounting. However, if you unfold this thing, it would be equivalent to the original, to the standard definition of a stochastic game, where there is no stopping probability, the game goes to infinity, and you are discounting the payoffs by a factor which is basically 1 minus the stopping probability that I just mentioned. The two structures are completely equivalent in terms of completely equivalent mathematically, but the way that I'm presenting it here is closer to how stochastic games are being used in multi-agent reinforcement learning, because in Marl, you typically have a stochastic games, which an episode of a stochastic game, and then when this episode is played, players change their policy, they update it based on what they learned throughout this episode, then they play a new episode of a stochastic game, and so on and so forth. And this is conceptually very important, because instead of playing an infinite horizon stochastic game, which lasts by definition an infinite amount of time, here you play episode by episode. So this is the Marl viewpoint. But other than that, in terms of equilibrium structures and all that, mathematically, the two formulations are completely equivalent. All right. So I don't know if there are any questions so far. Just please stop me whenever something doesn't make sense.
Yeah.
Yeah.
When we implement this randomized probability of stopping, I mean, it's not random, it's the probability of stopping. It means that the runs of the learning will be a random variable, correct? The t is a random variable when you take samples.
This t, absolutely. This is absolutely a random variable, yes.
You know how they normalize normally these payoffs, because if you compare them, you cannot take maybe you can, but I expect slower convergence. We have always a problem how to represent the reward in this scenario.
You can, if you're interested in the limit where, for instance, the stopping probability goes to 0, you might normalize.
It's just
Sorry?
about if you have a Q table or something, what do you put in that table in order to record the rewards? We thought of normalizing them to per period rewards to make them more comparable, but maybe that's wrong. I don't know. I mean, it's maybe a technical detail that depends on the particular learning method, but you see, because the run of each episode is random, it's harder to compare different episodes with each other. That's what I'm.
That is true. That is true. However, if you're not doing Q learning, but
Yes.
you are doing a policy gradient method, which is what I'm going to show here. In a policy gradient method, you record the policy, and the policy is a map from states to actions. And this is, of course, this can be equally huge, because maybe you have a huge state space. So then there is a question of how to represent succinctly a policy, but for a policy, for representing policies, you don't care. Rather, the fact that you have different episode lengths does not impact you in terms of storage or in terms of recording, because you only need to store a static variable which has dimension equal to the number of actions to the number of states, which again can be huge. But this curse of dimensionality is something that you also have in Q learning. So
thank you. Okay, thanks.
I don't know if this answers your question. Yeah. Okay, great.
Yeah.
Yes.
Yes, Yannick.
Yeah.
I was wondering, so if you just play an episode, so you play once, you know, there are real actions, and so how do you make sense of the expectation? You know, if you just play it once, I mean, where, you know, standard expectation means sometimes you will stop early, sometimes you will stop late, etc.
So if you just play once, what you will get as a payoff, it is this thing.
Yes.
All right. This expectation is defined over all possible trajectories that might lead to an episode terminating. Okay, so this value function is theoretical. You never actually observe this value function.
Okay.
All right. What you can only observe is this sum. That's it.
Okay, fine.
Okay.
Okay.
And I will be even more egregious in a moment, because not only will I be assuming that you actually know this function, but that you can actually somehow differentiate it. Okay. And I will do some very nasty things in this sense, but I will try to justify them in a bit. But you're absolutely right, and it is important to know that from a learning viewpoint, I mean, realistically, what players can only observe is this, and that's that. All right. So, Nash equilibrium policies in this context, and again, we're talking about stationary policies, are defined based on this value functions, as you would expect. And what is important is that you still have, in this context, in a first order characterization of Nash equilibria. What does this mean? That if the gradients of your policy, if the gradients of your value function satisfy a certain stationarity condition, which is the standard stationarity condition that you know from KKT, Karuskun-Tucker conditions. This is first order optimality. What this tells you is that if a policy satisfies first order optimality, then it is a Nash equilibrium. This, I will ask Stefanos to correct me, because I'm not sure. I know that they proved a version of this very important proposition in their work, in their paper. I'm not sure. I'm also citing here another paper which came in at I think at around the same time. And if you want to know more about the story, I defer to Stefanos, who is an expert on this. I am just very happy that this result exists, so we can use it. But the important thing is that in the world of stochastic games, we have this equivalence between first order stationarity and optimality, or rather equilibrium. Okay, there are some technical conditions which essentially boil down to we don't want the game to have any absorbing state, so we're working with ergodic stochastic games. All right. We can discuss them later if you want, but the gist of it is, and what is going to be very important for us is exactly this condition. All right. Now, in this context, what do? We can use rather, I mean, Bernhard already hinted at an important class of policies known as Q-learning. Another class of policies is policy gradient, where what you do is you take the gradient of your value function relative to your policy, and you just run policy gradient ascent on it. Okay, so you take a step and then you project back to your state of policies. All right, now, of course, this can be difficult because how do you compute this? Maybe you don't know it fully, so you only have some stochastic information for it. This is still difficult. What is important is that there is a certain technique known as the log trick, which is the basis of a subroutine known as reinforce. It is a classic estimator going back to Sutton and Barton in the 90s, which allows you to construct a stochastic estimator of your policy gradient based only on the oops, that's a typo. That should be based only on the observed payoffs at each stage. All right. We can go into the details of how this is defined later. What I want to show you is that, again, in this context, we have the same geometric high-level picture of equilibria. We have fully mixing equilibria, which for any state give a fully mixed strategy. We have just mixing, not fully mixing equilibria, which for certain states or certain players give a non-fully support strategy. And we have deterministic Nash policies, and which for every state give you the same pure action. And these deterministic Nash policies, generically, they are actually strict in the same sense as before, in the sense that the corresponding equilibrium condition is satisfied as a strict equality. And these equilibria satisfy geometrically the same condition relative to the normal cone, meaning that the corresponding policy gradients always live at the interior, the topological of the interior of the player's policy space. All right. Of their normal cone at the corresponding point in their policy space. And again, so we have two completely different frameworks, but the driving questions that we want to have to answer rather is when does learning, I mean, following policy gradient method lead to a Nash equilibrium? When does it not? And what other types of behavior emerge in the long run? Okay, and if I took this much time to explain these two frameworks in detail, is to show you that we start from completely different viewpoints. We have completely different starting points, finite games versus stochastic games, but the end questions that we want to answer are the same, and also the type of algorithms that we use in practice also kind of have the same structure in the sense that they all rely more or less on the player's individual payoff or value function gradients, their gradients, some sort of individual gradient at any case. All right, so these are the two basic unifying features that we want to leverage and exploit in order to develop sort of a unified view. The first is that we have continuous control variables. Whether the players are controlling mixed strategies or policies, these are all continuous control variables. They live in different spaces, they do different things, but they are all continuous and they are all under the control of the players. And second unifying feature, what I just said before, is that the learning is driven by the player's individual payoff gradients. All right, whether they are mixed payoff vectors or policy gradients. These will be the main ingredients of the unifying framework that I would like to present. And namely, we'll be talking about games with now continuous action spaces. We will introduce here an umbrella learning process called regularized learning, and the way we will analyze it will be based on stochastic approximation theories, which harkens back to the original work of Robbins and Monroe back in the 50s. All right. And well, that's what I'm going to try to show, sort of a unified stochastic approximation framework for learning in games. Right. So very quickly, we said continuous games. What type of continuous games? What is a continuous game? We still have a finite set of players. We have a closed convex set of actions per player, and each player has some continuous differentiable payoff function defined on the product of their action sets. All right, as we discussed already, this class already includes mixed extensions of finite games or stochastic games, but certainly much more than that. You have Cournot oligopolies, you have Kelly auctions, you have GANs, you have you have atomic splittable congestion games, certain models of non-atomic games, etc., etc. Many power allocation games, power management games. It is a huge class. Here, the notion of a Nash equilibrium is defined directly on the player's action sets, but otherwise you have the same defining Nash inequality. And what is going to be driving the process here is, again, the player's individual payoff gradients. All right. Before, in the case of normal form games, this was the mixed payoff function of the player. In the case of stochastic games, this was the player's value function. All right. And we still have the same first order stationarity condition. Now, here, however, because we have made no assumptions about individual payoff concavity or whatnot, we need to be a bit careful. If a point is Nash, then it satisfies first order stationarity. The converse in general does not hold, though it does hold if the player's payoff functions are individually concave. So if we have a concave game in the sense of Rosen. All right. Luckily, even though stochastic games are not individually concave, the result I alluded to by Stefanos and co-authors and that literature thread ensures that still first order stationarity implies Nash. So we are going to hone all our framework on achieving first order stationarity because this is what is going to lead us to Nash equilibrium, at least in a large class of games. All right.
Sorry, concave includes linear?
Concave includes linear, yes.
So what is nonlinear in the stochastic case, in the stochastic game case?
The fact that you are taking an expectation over the player's policies, so this completely delinearizes the dependence of the payoff function on the policy.
Okay, thanks.
Right. Now, in terms of feedback, this is where we get into the area of regularized learning. What does it mean? In terms of how to run our algorithm, we would like to have access to the full payoff gradient. We will not assume that. We'll assume that we'll have access to some black box model thereof. So what is a black box model? Maybe there is some zero-sum noise, and maybe there is also some bias. For the zero-sum noise, we will assume that it has a finite variance. And for the bias, we will assume that it is bounded by some deterministic sequence BT. And we will state our results in terms of these two parameters which characterize the type of feedback that we have. If we don't have vector type feedback, if we only observe the payoff that we got, then we have to somehow estimate it. There are techniques how to do this. Here I'm showing a technique known as SPSA, single point stochastic approximation. I don't want to get into the details of how you go from bandit feedback to vector-based feedback. If this is something that you're interested in, please ask me. At the end, we'll be happy to explain. But for now, I will just put all these under the umbrella of the black box model. I will assume this given and I will go forward. given such a black box model, what we do, we follow exactly the same thing that we did in exponential weights or policy gradients. We are taking a gradient step, and then once we take this gradient step, we take a projection of the result back to the player's action space. The only twist is that we're not taking only Euclidean projections. The Euclidean projection would be here if we had the norm squared. We don't assume just Euclidean projections, we assume more generalized projections, which are sometimes called mirror maps, and this is sometimes called mirror descent, the algorithm, or other variations of mirror descent or dual averaging. And it includes, certain, a very widely studied class of learning algorithms for finite games known as FTRL, follow the regularized leader. And of course, it includes special cases, exponential weights, and policy gradient methods that we just saw. And of course, a lot of other examples that I don't have time to cover, but I can show you a couple of examples later. All right, so these are our two basic ingredients. We have continuous games, and we have this type of regularized learning meta template, if you want, that we use to learn in this type of games. What are the results? All right, so I'll show you with a couple of pictures first. Starting with the simplest possible game, 2x2 games, Battle of the Sexes. And here I'm showing you the continuous time limit of the algorithm. So when the step size is very, very, very small and we have perfect feedback. And you see that in that case, these blue curves are converged to equilibrium. Now, almost all of them converge to strict equilibrium. There is just a measure zero of trajectories which converges to this mixed Nash equilibrium. Early work on the field by Josef Hofbauer and his co-author established the so-called folk theorem of evolutionary game theory, which tells us that this situation actually captures everything that can go on. In particular, the folk theorem tells us that strict Nash equilibria are stable and attracting, so they attract all nearby trajectories and they capture them. Nearby trajectories cannot just wander away and then return. Not only that, but strict Nash equilibria are the only states that have this property. And then you also have that, so in particular, mixed Nash equilibria like this one are inherently unstable, which means that all but a measure zero of initial condition will actually diverge away from this. And there are some other caveats. There are some other ancillary results in Josef's theorem that in the folk theorem that I don't want to get into right now. I just want to show it again in action here. In Prisoner's Dilemma, we have a unique strict equilibrium. We converge there. On the other hand, when we only have a unique fully mixed equilibrium, like in matching pennies, what happens is the game here is what is known as Poincaré recurrent, or actually in this case periodic, meaning that all trajectories cycle around the equilibrium, neither converging nor diverging away from it. All right. Things are start becoming a bit richer when we go into the class of 2x2x2 games, but again we see the same features. If we have a game with strict Nash equilibria, everything is attracted there. And if we have a game, for instance here, a game belonging to a class known as a harmonic game, this has a lot of mixed Nash equilibria. It is a non-generic game. And in this game, what happens is you have periodic orbits that cycle around this manifold of equilibria without converging or diverging away from them. All right. And then the thing is that you have the same inherent instability of mixed Nash equilibria. For instance, in a game known as Jordan's Matching Pennies, this game has a unique fully mixed Nash equilibrium. But then, as was shown by, again, Josef and his student, Andrea Gannersdorfer, I think this result goes back to them, is that all trajectories of this exponential learning, the replicator dynamics in continuous time, expand away and all converge to this limit to this heterogeneous limit cycle on the boundary of the simplex. So this is yet a different cycle phenomenon. Everything converges to this particular small dimensional set. All right. Under noise, things are different. I will skip this because I'm running a bit out of time, and I will just show this slide. Actually, I will show this slide, which tells you, should tell you the following. If actually this slide, which tells you the following, that if you have a certain behavior in continuous time, all right, so like in Battle of the Sexes, where everything converges to strict Nash equilibrium, then these points that are attracting under continuous time are also attracting if you're in discrete time and you have even noise or other types of uncertainty. So this is not a formal result. The formal result is as follows. To state it, actually, we'll need to talk about stochastic stability, which means that a set is stochastically stable when, with high probability, if your process starts near S, then it remains nearby. And stochastic asymptotic stability, which tells you that with high probability, if your process starts near the set in question, then it remains nearby and eventually converges to it. All right. So these are the two notions of stability, and the result is that if you have an attractor of the continuous time dynamics, like what we saw, for instance, here when we were talking about strict Nash equilibria, these are attractors, but these are not the only attractors. If we go to Jordan's matching pennies, then this heteroclinic limit cycle is also an attractor, okay? And this is a setwise attractor. Now, the theorem that I'm alluding to tells you the following, that if you have such an attractor and the black box model that you're using for feedback and your step size or any other parameter satisfies certain conditions. I don't want to get into the details of these conditions. Suffice it to say that these are conditions that are satisfied in all the models and algorithms that I showed you so far. Then, under this condition, this continuous time attractor is stochastically asymptotically stable under the entire range, the entire umbrella of algorithms that I showed you. All right. And if you narrow this down, because of course we're talking here about attractors of continuous time dynamics, which is a very difficult beast, we can narrow it down to points, and in particular certain classes of equilibria which are variationally stable, meaning that they satisfy sort of a variational stability condition around them, like the dual of a Karush-Tucker condition. Then, in that case, if you have any equilibrium which satisfies this dualized KKT condition, known as a local multi-variational inequality, this theorem tells you as a corollary that these equilibria are going to be stochastically asymptotically stable under the entire range of regularized learning algorithms that I mentioned. All right. And this theorem, this sort of meta theorem, is what explains why stable Nash policies are attracting in stochastic games and why strict Nash equilibria are attracting under exponential weight algorithms and their friends in finite games. I will skip here the slides that have to do with the rate of convergence. I know that there are a lot of you are interested in particular in the specific result that we get for policy gradient methods for stochastic games. And what I want to keep you from this, if you take this framework and you just narrow it down to policy gradient methods for stochastic games, then the outcome is the following: that if you have a stable Nash policy, meaning a Nash policy which satisfies this variational stability condition that I mentioned here, then this Nash policy is locally attracting with high probability, And if you narrow the things down a bit further, and you're talking about deterministic Nash policies, so stochastic games with deterministic Nash equilibria, which are generically strict Nash equilibria, then policy gradient methods converge to such strict Nash policies, and they do so in a finite number of iterations. This finite number of iterations is part of the slide that I just skipped about the convergence rate, and but we can go into it in more detail. The formal version of this theorem is a bit more convoluted, but I think I'll stop here. I had a couple of other slides to show some links that this meta theorem that I showed induces between dynamic stability, so asymptotic stability, and the strategic stability in the sense of Kohlberg and Mertens, and another result by Ritzberger and Weibull. But yeah, I think it's good to stop here. And if you have any questions, please go ahead.
Thank you very much, Panayotis. I think we started 4 minutes late, so if you like, you can still continue for a few more minutes, or if you feel like this is a good place to stop anyway.
I could. I don't know if there are any questions in the meantime, or I don't know if you have questions after the 1 hour, whatever works. I mean, I would be very happy to show you what I mean. It depends on, I don't know if there are any questions in the chat. I admit I haven't been paying attention.
Could I ask a question?
Yes, please.
What's the link between linear stability and stochastic stability?
Okay, so linear stability is a notion that has to do with continuous time dynamical systems and tells you that convergence will occur at a geometric rate. Okay, or rather, if you want that linear stability or linear instability means that unstable trajectories diverge away at a linear rate, at the geometric rate, and convergent trajectories converge at a linear or geometric rate. Okay. In the case of stochastic stability is something which has to do with, first of all, stochastic algorithms and discrete time algorithms. So the settings are not quite the same. You can examine whether the rate of convergence for a certain state is geometric or not, but because of the stochasticity, because we have randomness, it is very difficult to define this properly. So there is no immediate link between the two. However, what I should say is that if you have a point which is linearly stable in the continuous time limit of the dynamics, then this is very good news for the discrete time algorithm, because you can typically establish some sort of rate of convergence then in that case as well. So you can leverage it.
Okay. And I guess this might be a simple question, but what does it mean for a game to be ergodic?
Sorry, this is an excellent question. So there was some fine print I had here about a thing called the mismatch coefficient, and I was assuming here that the game has a positive mismatch coefficient. Now, the definition of this thing is a bit convoluted, but roughly speaking, what we want is that that for any given policy of the players, every state of the game is reachable starting from any other state. Okay, this is a simplification of what having a positive mismatch coefficient means. But this is this property that I alluded to is ergodicity, basically irreducibility, in the context of Markov chains. In the context of MDPs, it is usually called ergodicity, and thus a stochastic game in energetic stochastic games. An ergodic stochastic game is a game which has this property.
Okay, yeah, thank you.
Yeah. And what you want to avoid is stochastic games where you have an absorbing state. So, if you somehow end at this state, you never get out, and so the game you no longer mix. You're going to be playing the same stage game until the end of the world.
Mhm. Okay. So like
This is
single, unique, stationary distribution kind of thing, right?
no, you can have oh yes, okay, I get what you're saying. Yes. Sorry, I thought you were alluding to an equilibrium. Yes, if you from a Markov chain point of view, yes, that's what it would be. Mm,
I guess if no one's asking, I was going to say
yeah.
in your black box models, right? What kind of noise? How do you introduce the noise? Like, do you assume they're normal? What kind of
Mm.
noise kernel, I guess?
No, let me go there. Not any particular assumptions. The results that I'm stating, I mean, in this presentation, only assume that whatever the noise is, it has finite conditional second moments, and that's that. You can relax this further. You can say that you can have a finite qth moments. Or you can refine it depending on whether you take q to be greater than or less than 2. But the only assumption I'm making for the statement of the results in this presentation is the finite variance.
Okay.
Okay, I have one question.
Yep.
So in the stochastic game, when
Mm-hmm.
you say the learning, so
Mm-hmm.
learning can be when you don't know the policy of other player, okay?
Mm-hmm.
But there can be learning because you don't know the transition probability also. So
Absolutely.
does this learning capture both the phenomena or just that we don't know the policy of others?
So let me go to this slide. Yes, this is the slide that I wanted to. If so, there is, as I was alluding to, if you're using this subroutine known as reinforce, this is the reinforce algorithm of Sutton and Bartle. If you use this subroutine, then the only information that you need is to observe your stage payoffs stage after stage. So with this estimator, you don't need to know either the policies of other players or the transition matrix of the or the transition matrix of the game, or even your individual payoff functions. You don't need to know anything. You just get payoffs, by playing, and you're aggregating this following this particular recipe given by the reinforced algorithm, and that's that. You don't need to have any knowledge of the game. So it actually captures both of the cases that you mentioned.
Okay, thank you.
Can I
Yep.
ask a question?
Yes, please.
So very interesting talk. So it was in the middle of your talk, you mentioned that something about continuous action space.
Mm-hmm.
And then does all your result extend to continuous action space in this case?
So just to be clear, in the middle of my talk, I am introducing exactly the notion of a continuous game, so a game with continuous action sets. And I just said that mixed extensions of finite games and stochastic games a la Shapley can both be seen as special cases of this framework. If you're alluding to playing, having a game in normal form with a continuous action space, and then you are playing on top of it, with mixed strategies, as you would do, for instance, let's say, in a Minfield game, or if you have then these type of games where you're playing over infinite dimensional spaces is not covered by our framework, because everything here, all my action sets, like my continuous action sets, are subsets of RD, and any mixing has already been done. I'm not going to be mixing over a continuous action space.
Okay. Yeah, right. Thanks for clarifying this. I exactly confused this with the continuous action space and doing
Yep.
lifting afterwards. So
Yeah.
then if we consider such a continuous action space,
Mhm.
then does this the stability result of this ODE theory still extend to this case, or you foresee some difficulty because of this infinite dimensional nature?
So the thing is with infinite dimensional spaces is that morally speaking, you want to say that things should work, but then the technical difficulties can be can crop up in very unexpected places. And in general, it is a very difficult framework. So I would say I'm optimistic about it because I have seen some first results along this direction, and also because a lot of these results only require some very light structure in terms of the space, so duality or metricity or something like that. So I would be optimistic, but you know, that's
Okay.
all I can say. I'm sorry.
Yeah, thank you very much. Thank you very much.
Yeah.
Yeah.
I have a question
Yeah, Bernhard.
on a much more primitive on the multiplicative weights algorithm. Suppose I want to estimate a parameter based on my recent observation, and I'm now updating this parameter as a convex combination of what I just observed and what I had previously. So if that convex combination is a 50-50, I mean, it will quickly converge, but I mean, is that automatically a multiplicative weights update algorithm, or do I need something?
No. That's a different algorithm. I mean, if I understand correctly, you are saying you're estimating something and then you are taking some moving average and then maybe you're best responding to it or whatnot, correct?
Yeah, whatever. I mean, I'm trying to base, my reaction, for instance, on a certain model of my opponent.
I understand.
Parameters, and I'm just updating this as a convex combination of the past, and then it automatically discounts the past exponentially when I do this convex combination in each iteration. So I wonder whether
I understand. My suspicion is, but there are other experts here. I mean, Yannick or Joseph could say more. I suspect that maybe it would boil down. What you are saying could boil down to some version of stochastic fictitious play, but not so much here for exponential learning type algorithms. Why? Because here you have an aggregation. So these things are things that grow a lot over time. Whereas when you have an exponentially moving average or something like that, these are things that more or less stay bounded. Okay, so when you are doing an exponential best response to a moving average, this looks more like stochastic fictitious play than this type of thing where you're really reinforcing things and then taking a logic best response.
Yeah, thank you.
Yeah. I have no idea who's next. I see Janusz.
Yes, hello. Thanks for the talk. Very interesting. I was wondering, you have these dynamics for the continuous time, so the deterministic dynamics, I think. And there you can sort of identify some basins of attraction for the different equilibria. And then when you show the stochastic dynamics, they sort of follow it in a little, they kind of seem to follow it. Can you say something about some sort of stochastic basins of attraction under the noisy dynamics?
No, I wish I could, but this is very difficult. In the case of strict Nash equilibria, we can identify based on the minimal individual payoff difference. It is possible to identify some subset, some neighborhood of the point, such that if you start within this neighborhood, I mean, explicitly characterize this neighborhood, such that if you start with this neighborhood, then you converge to equilibrium with a given probability. So you can identify, in the case of strict Nash equilibria, a subset of the basin of attraction, but characterizing or identifying it in total, I have no idea how this item. I have no idea how to even start thinking about this question. Sorry.
No problem. Thanks.
Yeah. Tom? Yeah.
Hi, yeah, I was just wondering if you might just put up the Kohlberg Mertens results or give a reference to a paper with them in.
So yes, the result I was alluding to is, let me get to this slide just a sec. The result I was alluding to is this one, and this tells you that a span of pure strategy. This is a result which only concerns finite games. Okay, just to be clear. And it tells you that a span of pure strategies is stochastically asymptotically stable if and only if it is closed under better replies. Now, there was this closedness under better replies is a sibling, let's say, of a property known as curb, closed under rational behavior, which was, I think, first considered by Ritzberger and Weibull, who first showed a version of this result for the replicator dynamics. And these types of sets are exactly the minimal ones which satisfy the axioms for strategic stability posited by Kohlberg and Mertens. And in particular, they contain an essential component of Nash equilibria, etc., etc. So, if you're interested in this result and in this this equivalence between dynamic and strategic stability, I have in the end of my slides a full references section. It is this result is this one, and then you have the original result by Ritzberger and Weibull here, and Kohlberg Mertens here, if you want to look at it in more detail.
Thanks.
Yep.
Okay.
Yeah, Manda.
Yeah, I have one question. Like, to prove the convergence of all this algorithm, you generally use the variational stability as a tool, right?
In certain cases, yeah.
Yeah, and for the variational stability, typically you generally try to show for continuous action game, it's monotone or strictly monotone, right? But sometimes proving the strictly monotone is very difficult, like to take the Hessian and to prove it positive definite or negative definite. So do you know any like other type of stability that can be used to prove the convergence other than the variational stability?
It is
so because I know some game where we know the uniqueness of equilibrium, but we cannot prove the stability or the.
Well, you see, the problem is that uniqueness of equilibrium is in no way suggestive of convergence. Let me show you the example of Jordan's matching pennies. I think, yes, here. So you have this. This game has a unique, fully mixed equilibrium, but still play converges here. Actually, I think I have this might not be super clear here. Let me see if I can do a bit better. Just give me one sec. Zoom, zoom, zoom. Stop share. Let me try again. Show this in all its glory. Okay, so what happens in this game? You can, if you want, follow here the yellow, follow the yellow orbit, and you can see you only have a unique mixed Nash equilibrium, but still you see everything goes round and around and around and around this limit cycle forever and ever. All right. So having a unique Nash equilibrium even in very simple games, does not suggest convergence. And in fact, this equilibrium could even be strict, and you still might not have global convergence to it. But
Okay,
okay, if it's strict, you will have local convergence. So
no, like my question was other than the variational stability, do you know any other type of stability used in the games?
well, you can sort of play on the variational stability idea and, for instance, introduce some player-specific weights or modulate a bit the coupling instead of having the vector field and the ray that is leading to the deviation modulate this coupling function a bit. But I am not aware of a condition which is simpler to check in full generality. I mean, I'm not gonna lie, it is it is convenient to prove a convergence, but in many cases, it just shifts the weight, the burden of proof to a different condition. But I'm not aware of something better.
Okay, thank you.
Yeah.
I have a question.
Yep.
So is there an example of a game? So what I'm wondering about is, what we've seen so far is you take a discrete stochastic system and you can describe part of what will happen in the long run with positive probability with characterizing attractors of the of a suitably found deterministic continuous thing. Under what are there examples of games where it's not enough to know the attractors of the continuous system? Where I have a set that is, internally chain transitive or something like that is not an attractor, but it will be approached.
Yes, and unfortunately, a game may not have attractors, and then you end up with a mess like this. So here is a simple case of matching pennies. Okay, and actually, let me move forward a couple of slides. So if you have matching pennies in continuous time, you have this very clean picture of a foliation of periodic orbits. All right, now. If you run some deterministic version of these algorithms, if you run a vanilla exponential weights, then everything diverges out to the boundary. But if you run a more sophisticated variant of the algorithm known as optimistic exponential weights, everything converges here. All right, so this tells you first two things, that the predictive power that you have, from knowing that you have this sort of recurrence or internal chain transitivity, because all these sets are ICT, goes out the window. And since you mentioned ICT, why is this the case? Because not only is this set an ICT, but this entire annulus, for instance, is an ICT. Or all of this is also an ICT set. All right. And stochastic approximation will only tell you that you will converge there. So already you lose all predictive power in the deterministic case. And even worse, when you have this sort of recurrent behavior, this sort of periodic behavior, this type of deterministic, vanilla exponential weights bad, but if I'm smart about it, I will get convergence. All this goes out the window if you're in a stochastic setting, because in a stochastic setting, everything becomes a soup, whether you have your crude vanilla exponential weights or your sophisticated, smart, optimistic exponential weights. The moment you have a modicum of uncertainty, convergence goes bye-bye and everything is all over the place. Why? Exactly because everything is everything. The entire space is an ICT set, and there are no sufficiently small ICT sets. Attractors are very small ICT sets, whereas these ones are. Whereas if you have a recurrent system, they are not. Sorry, I don't know if that answers your question or if I
yeah.
went off a tangent.
This is very good. Thank you.
Okay.
Do you have more questions?
Maybe just going off of what Clement was saying, how about I presume things are still nice around stretch in there?
Sorry, come again. I didn't make up the question.
Sorry, I'm not sure whether it's the audio working. Can you hear us?
Yeah, I can hear you. I just didn't hear the question.
So just kind of what Clemens was saying, I presume things are still nice enough when you are talking about convergence to a strict Nash equilibrium in continuous time, and then go into discrete time from that and add in stochasticity as well. You still have some type of convergence.
Yes. Just to make sure, you're asking if things remain nice for strict equilibria when you start having noise and things like that.
Yeah.
That is exactly the well, I stopped the focus on stochastic games, but for finite games, you have exactly this very nice equivalence between strict Nash equilibria and stochastically asymptotically stable states under the entire range of these regularized learning algorithms in the presence of noise, stochasticity, uncertainty, and whatnot. Yeah.
Okay. And this is done by proving some type of Lyapunov function around the equilibrium?
Not really. For this particular result, I would say the analysis is a bit more ad hoc, and it uses, I mean, what I'm gonna say is extremely hand wavish here, so my apologies. But the thing is that if you're here in a neighborhood, then basically you see your payoff vectors will be pointing in the interior of this normal cone. So in a manner of speaking, your random process will have a drift, which is driving it deeper and deeper into the normal cone. And this is sort of the property that you leverage in order to show that when projected back to the simplex, you have convergence to the equilibrium.
Okay, thank you.
Yeah.
I have a question. Right,
Yep.
one way to show like that it's stochastically stable is that the unique absolutely continuous invariant probability measure is centered on that strict Nash, because you can break down your stochastic update into a discrete step and then like some convolution around that point. Like if you think in terms of probability measures, does that make sense?
I'm not sure I follow exactly.
So like you can treat like your stochastic update as a deterministic step, and then you convolve that probability measure around that area, and then that becomes your new point. And then if you show that the unique probability measure is centered around that strict Nash, then you show that it's stochastically stable. Or am I just overcomplicating this?
Perhaps I wouldn't say overcomplicating for sure. I would say that I'm not I haven't seen this approach. I don't know. I don't know if it can work. And if it does, it will be super interesting. I cannot tell if it's going to be simpler or not. I just haven't seen this approach. So I would actually be very interested. To if you want to explain it in. I mean, let's take this offline if you want to explain it a bit more. I cannot say if this can work.
Yeah. Yeah, never mind. Yeah.
Maybe just a short question to clarify this, the notion of stochastic stability you're using is not the same as the Peyton-Young one, right?
Absolutely not. Absolutely not. It has nothing to do with that. This is the notion of stochastic asymptotic stability and stochastic lack of stability that is being used, for instance, in stochastic processes, in stochastic analysis, etc., Hasminsky, etc. No, it has nothing to do with stochastic stability or what you have in coordination games and who else it is? Gilboa, Matsuri, I don't remember who else. It is not that type of stochastic stability. No.
Okay. So if there are no further questions, let's thank Panayotis again for his patience and very clear presentation. Thank you.
Thank you for having me.
Yeah, thank you.
Thank you. Great pleasure. Great pleasure.
Bye.
Yeah, I